So in this video, I'm going to be talking about random errors, precision, systematic errors, accuracy, reliability, and validity to help you with your experimental practical report. So, random errors are caused by any factor that randomly affects the measurement of a variable. So this could include the use of a timer. Sometimes when we're timing something, we're going to be a little bit too high, a little bit too low. So there's going to be that random fluctuation around what the real measurement is. And basically, so the amount of random error is reflected in the amount of scatter. So when you're looking at your trials, if there's scatter, there's going to be random error present. And what we can do is we can increase the sample size or the number of trials. And what that allows us to do is we can take an average, because sometimes you're going to be a little bit above and sometimes you're going to be a little bit below the true time. So by doing multiple trials and calculating average, that's going to reduce the effect of random errors and make your results more reliable. So increasing the sample size, doing even more than 3 trials would reduce the effect of random errors even more and make your results even more reliable. But you do need to know that measurements can never be done perfectly, and therefore you can't actually eliminate random errors. So it'd be wrong to say that calculating an average is going to eliminate the random errors. It's not. It's going to reduce the effect of the random errors. Now, precision is how consistent the results are when the experiment is repeated. So basically, in your data tables, if you have your I'll explain. So basically, precision depends on how well the random errors are minimized. So if you have minimal random errors, you're going to have minimal scatter. So random errors cause scatter in your data. And basically, if there's scatter, that's going to influence the precision of your data, because precision is how consistent your results are. So if you have this is the main part. So if you have lots of random errors, that's going to result in high scatter in your data, which means that you have low precision. And if you have minimal random errors, then you're going to have low scatter from trial to trial, and therefore you have high precision. So it presents this precision random errors. You can identify it in 2 ways in your experiment. So one in your data table. So from trial to trial, if there's scatter, then there's random errors, and then there's less precision. But for argument's sake, you might have, if you look at your data table for 50 grams, they might be really close together. And as you go down your data table, as you're adding more masses and force, you might have more scatter. The timing results might be more spread out, more scattered. So because as a car was getting faster and faster, it's harder for your timer to accurately record accurately get the time measurement. So your scatter might have decreased as the car got faster. So you need to talk about your the interplay between random errors and precision in your experimental report. Another way that you can identify whether there was random errors in your experiment is if you look at your graph and there is scatter around the line of best fit, that means that there are random errors present. If there's no random errors present, your points for each force applied would be exactly in a straight line. So force and acceleration are directly proportional to each other, which means that they should be a straight line through the origin, but obviously your results aren't going to look like that because there's going to be presence of random errors, which is causing scatter and imprecision in your results. Now, systematic errors are different, and what they differ your results consistently from their true value. And systematic errors are usually linked to faulty apparatus or incorrectly calibrated. So it might be reading, the scales might be reading 550 grams, but in reality, the scales are out by a couple grams. So they're always giving you a reading that's a couple grams too high, a couple grams too low, but it's going to be a consistent error. So systematic errors are when it's an error that is consistent from the true value. And taking an average does not correct the problem or give a more accurate result. Okay, you can't eliminate systematic errors like that. What you can do though is if you repeat an experiment and you might swap out a piece of equipment, and if you get the exact same results, then that identifies that piece of equipment is not the source of the random error. But you can keep swapping out pieces of equipment and keep repeating it to try and work out what is causing the systematic error. But it's not always just a faulty piece of equipment. It can be the design of the experiment. There could be something else causing a systematic error. Now, evidence of systematic error shows itself in graphs as a y-intercept. So it doesn't make sense for this straight line to go through. The y-intercept's approximately 0.35. It's a bit blurry, but it intercepts the axis about 0.35. So it doesn't make sense to have a force of 0.35 on a trolley and to have zero acceleration. If you're applying a force, there's going to be some acceleration. So obviously there's some sort of error here. So some sort of systematic error. So if you think about it, how can there be a force acting on the trolley but not causing it to accelerate? I'll let you think about that. But yeah, there is a systematic error causing there's systematic error. So there's some force acting on your trolley that's not causing it to accelerate. So basically, accuracy is how close you are to the true value, and systematic errors cause inaccurate results. And in the context of your experiment, you're trying to verify Newton's second law of motion, that is, the force applied to an object is equal to the mass of the object times by the acceleration of the object. So you were changing the force and measuring the acceleration. And so if you look at your graph, you have force and acceleration. And the equation of a straight line is y equals mx plus c, where c is your y-intercept. And remember, y-intercepts are systematic errors caused by systematic errors. M is your gradient, which is your slope. So you can get the equation from Excel, and this value here, the 0.2778, is your gradient. And what's on our y-axis? On our y-axis is actually force. So on our y-axis is force. Our gradient is going to be the mass of the object, and on our x-axis we have the acceleration. So if you compare your mass to your gradient should actually be equal to the mass of your trolley. And how close together these values are is how accurate your experiment was. The last thing I'm going to talk about is reliability and validity. So reliability is all about getting consistent results. So is the extent to which outcomes are consistent when the experiment is repeated more than once. So obviously this is why you're getting multiple trials. So if you have random errors, they cause scatter and that low precision. So basically random errors reduce the reliability of the results. So when you talk about reliability, if you have high random errors and there's high scatter in your results, then you would have lower reliability. But if you don't have much scatter, which means you have minimal random errors, which means you have high precision, well then you can say that you have high reliability. And validity is all about whether the measuring devices that you used actually measured what you wanted them to measure. So were the results from your experiment valid? And basically systematic errors caused by incorrectly calibrated measuring devices or that experimental design can lead to inaccurate results. And hence, systematic errors cause inaccuracy, and if there's inaccuracy, then the results or your conclusions are less valid. So hopefully that gives you a bit of an idea about random errors and how they link to precision. Like random errors cause scatter, which leads to low precision, and precision and random errors relate to reliability. And then systematic errors can cause inaccuracies, and if there are inaccuracies, then your experiment is less valid. So that's how they all link together. Hopefully this made sense. Cheers.